guys, so today we're going to do a little bit on groundwater. And before we can do that, we first have to learn about a couple of terms that I have on the board up here with me. So the first one that we're going to talk about is porosity, okay? And porosity is the total percentage of empty space inside the soils, okay? Now what that means is that soil or ground, anything in the ground is made of particles. And we're going to just pan over to this little situation that we have here, because what you can see is I have a bunch of columns with different sized particles in them. Not including this one, but if we look at these three, what I notice is that there's little spaces in between all the particles. And believe it or not, the porosity of these columns is about 40%, which means that within that column there's about 40% space that is just filled up with air right now. So that's what porosity is. It's the amount of empty space that you have in the soil, in this case in a column of these little plastic beads. Okay? The next term is permeability. Now, just keep in your head, when we think porosity, we think amount of space. When we think permeability, we think flow. Okay? Permeability is the ability of water to pass into or through something. Okay, I'm going to move my eraser out of the way there. So when you think of something permeable, you can think of a screen on a window, for example. A screen is permeable to air, right? The air can flow through, but it is not permeable to bugs. It is not permeable to other objects that you don't want entering. The same thing can be said for different types of soil on the ground. They are permeable to some things. They allow a lot of flow. And it really depends on the type of soil, you know, the characteristics of that particular soil. Okay, so that's permeability. Next up and last is our capillarity. Last year in life science you may have learned a little bit about capillarity, and basically what it means is this upward flow of things. We've learned in the past that water has attractions in it that cause the molecules to attach to each other. And that causes the water to actually flow up against gravity. And that becomes a really important concept in groundwater. It's the upward flow of water through tight spaces. Alright, so now we just kind of had a basis term. We talked about what porosity was, we talked about what permeability was, and we talked about what capillarity was. Now, let's kind of put those into a diagram. Let's make some sense of what those things actually mean. Okay, so the first thing that we need to do is understand that we've got rain falling, right? The rain's coming out of the sky from clouds, and it's going to hit the ground. Now, when it hits the ground, a couple things could happen. Perhaps it's hot outside, and I'm going to get a lot of evaporation off the ground. So maybe a lot of the rainwater won't even stay on the ground. It's just going to evaporate, and it's not even going to look like it rained, right? Another option is that the rain is going to hit the ground, but then it's going to move along the ground. Maybe you're on a hill, and it's going to slope down the hill. That's called runoff. We see that all the time. But the third option, which kind of is the one that we're most concerned about, is what's called infiltration. Now, to go in something means you're going inside, right? That's what in means. Just keep using the word in here. So when I'm infiltrating, the water is going into the ground. Okay, so what I'm going to do is I'm going to kind of draw. Oh, that's really large. Let's back on that for a minute. I'm going to draw water infiltrating into my ground, just like that. Now, eventually, what's going to happen is it's going to make its way all the way down, and if you had a shovel and you had the time and the ability to dig, you would keep digging until you hit solid rock, right? Impermeable rock that water cannot flow through. We talked about this idea that permeability is the flow of water. So we're going to hit this rock, bedrock, that is impermeable, meaning that there is no flow of water through it. Okay, there are no pore spaces in that rock that allow water to flow. So that water is going to go all the way down until it hits that bedrock, that layer of bedrock, and it's going to start to build up. So the reason that it will build up is because now this whole layer of rock here is permeable. There are pore spaces, like we saw in our little column of little plastic balls before, that allows water to sit in them. So it's permeable. So what's going to happen is the water's going to flow, and it's going to flow up to a certain point. Whoops. It's going to flow up to a certain point. And that point, let's say that point is right here. So now we've got two distinct places in this one layer of rock. The point at which is completely filled with water, all those pore spaces are filled with water, that is known as our zone of saturation, because it is saturated with water. Just like a cloud is saturated and then precipitation comes out, that is saturated with water, which means that it is a zone of saturation. Above that, though, there's not always water in the pore spaces. In fact, there's air in the pore spaces. So we call that our zone of aeration. Okay, the zone of aeration. And a very important term, not just for earth science, but just for being aware, especially on Long Island, considering it's directly below us and very extra important compared to other places, is known as our water table. And that's what this blue line represents. So I'm just going to write it here. That, oops, keep messing up the pen here. That is called our water table. Okay? That is the water table. Couple of other things that we should just kind of think about here. When you have a drought, right, you don't have a lot of rain. So what happens is that water table comes down. Okay, we're going to shorten the width of our water table here because there's not a lot of available water, so the water table comes down. On the converse, when we have a lot of rain, the water table is going to rise, and it can actually rise so much that now it's going to hit the surface. And now if my water table is at the surface, I don't have any more infiltration because the water table is at the surface. There's nowhere for the water to infiltrate into. So what's going to happen is it's going to run off and you're going to have a flood. And that's the danger when there's serious rains for long periods of time, because now the water table has reached the surface and there's nowhere for that water to go, so it must just pile up and lead to flooding. All right, so we have, proper grammar here, one more zone that we must discuss here, and that is called the zone of capillarity. But before we actually define what it is, we need to talk about what capillarity is. It's this upward movement of water. And what I'm going to do is I'm going to add to that definition. I'm going to say it's the upward movement of water, and it depends on the size of the particles in whatever layer you're talking about. So let's think about where this is all happening. Here's my zone of saturation, right? And here's my zone of aeration. So I have water in between all the particles below this line, the water table. And above this line, I have air in my particles. Air in between the spaces of my particles. So what that means is that I'm going to have capillarity, the climbing of these water through those tiny little spaces right here, because they're now going to move from where there's water in the spaces to where there's air in the spaces. So I can draw a little arrow here to kind of represent my upward flow of water molecules through the empty pore spaces, or I shouldn't say the empty pore spaces, I should say the pore spaces that are filled with air. Now, if I have really, really small pore spaces, tiny, like in a clay, for example, I'm going to actually get greater capillarity. So my zone of capillarity, which actually let me define that right now, my zone of capillarity is the width of how much those particles travel up. Okay, so if I'm talking about my zone of capillarity, I'm talking about the distance between from when the water molecules start to travel from the water table to how high they go. So we're going to call this the zone of capillarity. Okay, and what I was just saying is if you have smaller particles in your zone of aeration overall, the zone of capillarity will become wider because the water particles can travel up higher. If the particles are larger, like a sand for example, they won't travel up as high. As a side note, in terms of plants, if you have a plant growing on the ground, the roots pull the water out of the zone of capillarity because there's some water moisture in them, but there's also some airspace. If the roots were extended all the way into the zone of saturation, they would rot because they would just be constantly submerged in water, and that wouldn't work. Okay, so the last thing that we're going to do right now is learn about to actually visualize what we just created. We just drew, a column, and a bunch of layers of rock and layers of earth materials, we'll just say, and we looked at them and we saw, kind of we diagrammed what everything looked like. But now we're going to actually put it all together with a demo here. Now, we're going to, instead of using the term soil, we're going to use the term regolith. Because soil is awfully specific. It refers to a certain amount of decayed matter as well as other non-organic components. So instead of using that word, we're going to use the word regolith. That is the geologically approved term for this topic. Okay. So with that being said, we've got our regolith here, and at the very bottom, I've pinched off this column because what I'm going to end up doing is I'm going to pour water through it. I'm going to make rain go through this column here. Now we can represent the very bottom as the impermeable bedrock below, right? Because we know that there's not going to be any water coming through this one particular area. Okay. So what I'm first going to do is I'm going to make some rain. So I'm going to pour my water in here, and we know what's going to happen. We're going to see some infiltration. So I'm going to pour my water in. I have to pour a little bit more. Let's give it a little bit more. A little messy, but that's okay. Alright, so now, a couple of things. We saw our infiltration, right? It rained, it went down through this, here's the ground level, the surface, went through the ground, and ended up here. Now, what I notice is that I can make a mark right here, right? And I've got two clearly defined layers. I have layer A above, now below. Now I'm going to actually kind of write this on the side here. I have layer A right here, and I have a layer B. Now, when I look at my layer A and my layer B there, I notice something. I notice that my layer A is all the spaces in between those particles, all the pore spaces there, that's all filled with water. On the other hand, in layer B, there are no spaces filled with water. There's a little spilling on the outside, which is why you see that all those little blue dots. But focus on the fact that you see water up to this point, and you really don't see any more water in the pore spaces here. So what can we call this layer where we have just liquid in the pore spaces? I'm going to give you a second to think about that. We call that the zone of saturation. Now, above that, we have another layer without water in the pore spaces. And once again, I'm going to give you a second to think about what that is. That would be called the zone of aeration, okay, because there is no water in there. And the little line in between is our water table. Now, what would happen if I got a lot of rain? If there was a lot of rain on a particular storm, let's say it was a nor'easter or something. Back up a little bit. What I notice now is I see that my water table has risen. Okay, it has gone higher. Now, if I continue to add water, what would happen is eventually I would get the water to reach the very top, and then I would have a flood situation, kind of like what we just talked about. So, as I added water, my water table climbed, so now I have a wider zone of saturation and a smaller zone of aeration. And I can add in here that in the ground, where especially where you had smaller particles, because these are fairly large, you would see a zone of capillarity, and you would see water traveling up the column. We just don't see that here because, as I said before, when you have larger pore sizes, pore spaces, you don't have as much capillarity. Much smaller, like if I had clay in here, you would see some of that capillarity.